Hello everyone, welcome to this stream. I'm Quinn, I'm a coach at Major League Hacking. We're going to be doing a workshop today on predictive uncertainty and detecting outliers. Really, we're going to be focusing on the idea of out of distribution data, and when we see data that we haven't trained our model on, how can we deal with that? How can we flag it? How can we identify it? And if we have the time, maybe we'll build a little app to do that for us. Little dashboard, perhaps. So welcome. I'm really excited. I hope you are too. I hope you had a good time so far in the Data Global Hack Week. I think this is still day one, right? This is day one. So hopefully your day one is going well. I'm actually not sure how many streams are left after my one now. But I think, oh yeah, there's one stream just immediately after this one finishes. So day one is nearly done. I hope you've had a good time. I hope you're looking forward to the rest of Global Hack Week. Please do check in. I put the link in the chat earlier, and for anyone who's kind of joined since then, I'll pop it in again. I'm wary that I know the Twitch ads can be quite brutal at the moment, so maybe we'll give it a minute or two before we kind of get really stuck into things. So definitely do check in. For anyone who's new, checking in gets you loads of things. It gets you points. And if you check into, I think it's 5 live events like this one, you can get swag. So if you want to know all about that, you can check out the Global Hack Week website. It's got all the details. The FAQs explain it all. But definitely do check in. And I think it will happen pretty automatically as long as you've got your address on the system. So do that. Get yourself some cool swag. I think there's stickers. I love stickers. Anyone who's seen my laptop, let me share it now. While we're waiting for people to join up, I've got like ooh, doesn't like this. There we go. Some stickers. I love my hex stickers. So yeah, that's why you should check in. Definitely do check in. Okay, and today's workshop hopefully is going to be pretty beginner friendly. My workshops tend to be a little bit more theory based, so I hope that's going to suit you all. We're going to talk through a bit of the kind of conceptual understanding, and yeah. It should be good. I'm not going to assume that you know anything. So as long as you've kind of got a basic grasp of Python, you'll be completely fine. We're going to be working in notebooks, and if you want, you can use Colab, but you should be able to run this on your laptop or computer or whatever you've got. So probably not on your phone. If you're on your phone, you might be stuck. But other than that, it'll be great. So yeah, pretty excited. Maybe we'll get started soon. Let me know where you're all tuning in from as well. I can, by the way, I've got 2 screens. So if I'm looking like here, I'm not ignoring you. In fact, I'm reading the comments. If I'm looking here, I'm looking at my code. So that's how it is. I can see we've got some hellos in the chat. Welcome. I'm glad to see that there's some excited people. Or maybe this was for the stickers. Probably the stickers. I love the stickers too. Someone joining in from Kent. Awesome. Someone's calling me R coder. I do quite a lot of R. All of this will be Python. So yeah. Right. Okay. I think we should maybe start pretty soon then. What I'm going to do is I'm going to talk through some of the theory, and then we'll get into some code. But I think first it's worth knowing the theory. Is there a GitHub repo? There is not. There is not. So for anyone who's new to my streams, I tend not to put things on GitHub because I want people to code along. I might towards the end, especially if we kind of get tight on time, push to a repo and share it, but probably not because we're going to be working in just one notebook. The file structure is really simple, so it should be fairly straightforward to keep up. I'm going to try and keep all of the ideas pretty concrete and visual. This is not like a maths class, but the theory is important when you're dealing with data, in my opinion. And so we're going to talk about some ideas. Yeah, pull open your VS Code if you want to be ready. I'm going to talk for a bit about some bits and pieces, and hopefully everyone will follow along well. And then, yeah, we'll get into the actual coding. But first, I want to maybe this is a good question we can ask to the chat. What do we think a prediction is? Let's say we've got a classifier and we've got some data and we see a data point and we want to identify whether it belongs to one class or another. So we've got a classifier. What do we think? Or like, what do we think a prediction is? Anyone in the chat feeling brave? I know there's some lag, so I'll give you a minute. I'll give you a minute to answer. Okay, maybe I'll go for it. No answers so far in the chat. That's okay. We're a bit shy today. That's fine. So a prediction is a number. And for example, if you had some data, let's say you had an image classifier, right? You might have a probability associated with how likely you think it is that an image is a cat or not. And that probability, you might be like 92% sure. That is your prediction, right? You have some kind of score. These are called logits, which expresses the likelihood of different features, for example, being present in an image, and one of them might be a cat, right? That is prediction, okay? And predictive uncertainty says when we make a prediction with a model, when we say like, oh, this is a cat, we've got some probability associated with it being a cat or not, right? We might think, okay, there's a 0.1% chance it's a cat. We might say there's a 99% chance it's a cat. Predictive uncertainty asks, how certain are we? How certain is the model about that probability? So if we've got like a prediction that like, oh yeah, 90% probability that it's a cat, but actually that probability itself has very low certainty, then our model is not sure, okay? And so there's two different types of uncertainty. Okay, the first is called aleatoric uncertainty, and this is irreducible noise in the data. So if you had loads and loads of different photos of cats, and like one of them maybe it doesn't have whiskers because the resolution of the photo is too low, or maybe half of its face is covered, or whatever. If you think about like MNIST, for example, if you've come across MNIST before, it's a data set with numbers in it. If you have an image of a number that's just really ambiguous, right? Like it could be a 3 or it could be a 5 and it's a bit blurry. That is called aleatoric uncertainty. Even a perfect model would be unsure, and it should be unsure, right? Because we don't know. If we looked at it, we wouldn't know. That's the whole premise. And then the other type of uncertainty, and this is the one that we care about, it's called epistemic uncertainty. This is kind of like your model ignorance. So if you trained your image classifier on cats, but you only had photos during the daytime, and then you gave it an image of a cat at nighttime, maybe the model should be unsure because it's never seen a cat at nighttime before, right? And it might correctly guess there's a cat in the image, but its certainty should be lower because it might not be, it might not have picked up the right things during training. And this is called epistemic uncertainty. This is where the model sees something which is out of its training data, and it should identify like, oh, I'm not sure. Okay, cool. Hopefully that makes a little bit of sense to everyone. So we have these two types of uncertainty. An epistemic uncertainty is when our model is ignorant to the data that it's seeing, right? Okay, cool. So most of this workshop, I know the name is detecting outliers, but what we're mostly going to be looking at is out of distribution data. Yeah, that's exactly right. Epistemic versus aleatoric uncertainty. Perfect. So most of what we're going to be looking at in this workshop is out of distribution data. So this is the idea that we have some inputs into our model, like a new image, which doesn't look like the training data. Okay, so we might have, I don't know, a new like sensor. If we were doing some kind of like data processing with like signals or something, we might have like distributional drift, or we might be, you know, seeing, like, for example, if we've got loads and loads of photos of cats and dogs and we're doing image classification of whether it's a cat or a dog, and then in, you know, the real world, our camera sees a goat, right? This is out of distribution data. It is data that it hasn't been trained on. And the goal for us, this is kind of what we're going to be focused on today, is that our models should be less confident. If it sees a goat, it shouldn't be like, I am 100% sure this is a dog. It should not do that. It should flag or abstain more often here from giving a prediction, or at least from giving a confident prediction. Okay. We also have in distribution data. So this is like when we see data in the real world, but it's only like what we've seen in the training set. So we have the same population or the same sensor, you know, the pre-processing is all the same, there's no drift. And so we can calibrate and set thresholds using this data. We also have outliers. Now, outliers are slightly different, and we're not going to look at them too much today. I know the name on the workshop says detecting outliers. Really, we're going to be detecting out of distribution data. But they might look like out of distribution data, but they might not be out of distribution. They might just be unusual data. So, for example, if you look at people's heights, an outlier might be someone who's 6'7", okay? And that's not out of distribution. They are still on the normal curve of heights, okay? We have a distribution. It's just a line that describes what most people's heights are like. So most people are like somewhere in this bell bit in the middle, and then either ends are, you know, less likely. These might be more like outliers, okay? Great. So we are primarily building an out of distribution aware pipeline. And we're going to be using predictive uncertainty, this idea that we have some quantifiable way of expressing how confident our model is. And we can do outlier scoring as well. If we get time, we might get onto that. But it's not the main thing that we're caring about here. Okay, cool. So I think now probably what I'll hop across to is VS Code. I know everyone's excited for that. And let me share my screen. Perfect. Okay, so I'm in VS Code. If you are new to programming, it is our IDE. This is where we write all of our code. It's where we have our terminal, which is here. I've just popped that up, and we can do all sorts of things with it. But at the moment, I'm not in a project, and I need to be in a project. So I'm going to open up a new project, and I'm going to do that by going to my projects folder, and I'm going to make a new project. So I really recommend you do this. You can see all of the lack of cleanup that I've got here. I've just made another new one. That's fine. And I'm going to call it Outlier Detection, or just DET for short. And I'm going to select that folder. And hopefully you can see this. Yeah, perfect. We don't need Copilot for now, although we do like Copilot, of course. And I'm now going to pull up a terminal. And we're going to create a quick virtual environment just to dump everything in. I might just give it a moment for people to catch up. I know I can go a little bit quick sometimes. So let me know once you've kind of got VS Code open, and hopefully you've got yourself in a project. I'm going to very slowly keep going. think most of this should be fairly simple to follow. So if you are familiar with Python, you've probably heard of virtual environments before, and we're going to make one of those now. And this just helps us keep all of our packages nice and separate so they're just in this project. And I'm going to use this little keyword called prompt, which means that we can name it something different in our terminal than the actual folder up here. I like to do this just so it's clear what environment I'm in. And so we can do that by typing this command here. Let's see, some people are caught up. That's good. Loading their virtual environment, that's fine. You can use conda as well. Conda is very popular. You can use what you like, but this is how I like to do it. And we can see we've got a little folder up here called .vmv. Perfect. Okay, and now we need to do some pip installs, and I might paste these into the chat because I'm sure it will be a bit tedious otherwise for everyone. That should be all of them. Okay, so I've just popped the command in the chat. You can just copy and paste that. It's in YouTube and Twitch chat. I'm going to type it out because why not? You can have this -q flag here. This makes it quiet so it won't fill up your terminal. I'm actually going to leave that for now because sometimes these installs can be a little bit funny with dependency stuff. Okay. Perfect. So we want NumPy, we want pandas, scikit-learn, matplotlib, and we've got a couple of libraries which we use for building Bayesian models, which is going to be fun, and I'll get to that in a bit. Okay, so if we run this, it might be a little bit upset with us. It will work it out. All right. And it's installing, it's installing. This is great. Perfect. Okay. So I've got some errors here. Can anyone spot what I've done wrong? This is a good thing that it denied it. So I didn't actually activate my virtual environment. Normally VS Code activates it for me. I must have told it not to at some point. So we need to fix that. I'm just gonna check that everyone's kind of caught up. Or maybe give it a minute or two. Let me know if you're kind of happy and at the same point as me. Okay, I'm going to keep moving. So to activate my virtual environment, I'm going to type this. And this will vary depending on the terminal that you're using. I'm using Bash, and also the OS that you're on. I see some people just catching up, only just arrived. That's completely fine. We've just made a project in VS Code, and we've got a virtual environment. You can use Conda or whatever you like, but this is what I'm using. If you wish, yeah, you can use Conda or something else. If you are on a different OS or terminal to me, this will look different for you. Probably most of you will have this looking different because I'm using Git Bash on Windows, which is a bit of a weird combination. As far as I can tell, most people don't do that. That's fine. But now I've activated my virtual environment, which VS Code might have done for you automatically. I'm going to do those pip installs again. And so those are in the chat for anyone who wants to copy and paste them. But they are NumPy, pandas, scikit-learn, matplotlib, others, PyMC, and ipykernel. And it will install this time without all of those nasty warnings and errors, which is good for us. Okay. Cool. Okay. We'll leave it to install for a little bit. So the first thing that I want to do is visualize what we've been talking about so far. And so we're going to generate some data. We're going to have some training data, some test data, and the test data, we're going to have two different sets. We're going to have one set which is in distribution and one set which is out of distribution. i.e. we're going to have a set which matches the pattern, the distribution, the line that is described by our training data, and one that does not. And hopefully by the end of the workshop, we'll be able to build a model that is capable of not just matching and doing classification, but also actually identifying when it's not sure. So that will be pretty good. I'm going to be pretty pleased if we can get some nice plots out by the end of it. That's my kind of end term goal. And I hope you're all on board for that. Okay, my installs are taking ages to run, but that's all right. That's just fine. Cool. We're going to use the same data throughout the workshop as well, just as a heads up. So this data that we're going to generate now, we'll use the whole way through and compare different models for. So what I'm going to do is I'm going to make a new file here, and I'm going to call it, we can call it just like OOD, let's just call it detection tests. I'm doing it in Colab. That's completely fine. If you're in Colab, that's not what I want to do. If you're doing it in Colab, there's some things which you probably won't have to install, like NumPy should already be installed, for example. There'll still be some bits which you will have to. But let me know if you have any issues. Hopefully we can work them out. But it should all be fairly straightforward either way. Okay, cool. So I actually don't want this. Let's delete that. Oh no. Don't want to be in there either. There we go. Okay, and we're going to call it, let's just call it detection, IPYNB. So this is a Python notebook, and I'm going to click enter, and now we've got a lovely little notebook. And so I'm going to create a section, let's call this section 1, and we'll give it a description. Generating our data, a small data set with in distribution, which we label as IND, data points, and a clearly separated out of distribution, or OOD, you've probably seen that before, and a clearly separated cluster that we will use to test our model's performance on unseen data. Okay. All right. And hopefully everyone's kind of got to this point. We can see that my installs have finished. This is great. And so our installs are finished. So this is not what we want. We want a code block, and we want it to be Python. And let's pick our environment because we haven't done that yet. And there we go. That's much better. We can see down here now that it's working in Python. Okay, brilliant stuff. So let's first deal with our imports. And yeah, imports and setup, I guess, but imports is fine. Okay, and we're going to want, as you can probably guess, NumPy. This is how we can manipulate arrays really nicely and efficiently and easily. And we want pandas. This is how we can manipulate data frames. And we're going to be using matplotlib.pyplot as PLT. We could use Seaborn. If you're a Seaborn fan, you could use Seaborn. It does produce some really nice plots. We're not going to, but you're very welcome to do so. And we're also going to import scikit-learn's datasets library. And we're going to import make moons, which is a function that will allow us to make moons, which is just a shape of data. And it's going to be really nice to demonstrate what is in distribution data and what is out of distribution data. Okay, and we're also going to pull in train test split. This is again like kind of just a tool for us to manipulate our data a bit better. Okay, and we're also going to do like some general setup. So let's call this imports and setup, and we'll call it like 1. Let's keep this nice and clean. Okay. All right, and the first thing that I want to do is I want to set some of our parameters for our plots. This is for our figure size. This is actually definitely what we want. This should be okay. These might be like a bit big. I'm going to make them these dimensions. We're going to be doing like a couple of plots, sometimes side by side, and so picking these out will hopefully give us some nicer aesthetics. And I'm also going to just set some of these bits. As far as this is going to give us some cleaner output as well. Okay, and we also in our setup want to set the seed, and let's do that using np.random.random state, and I'm going to use 42 because that's what I like. Cool. So this is all pretty standard setup stuff. Hopefully it kind of makes sense to you all. Perfect. Okay, right. And the next thing that we need to do is actually make our data. So let's do that. So we're going to type, generate our IND, data. This is our in distribution data. Okay, and so we're going to be making 2 interlocking, half circles, also called moons. Perfect. Okay, and so we're going to have x all, and then y all. And the reason this is like good is because it's non-linear. Realistically, most data is not linear, and this is going to be a slightly more engaging example than just your standard linear data. And this is a classification task. So instead of using, for example, linear regression as our model, we are going to be using, I don't want 0.1 there, I want 0.2. And yeah, we're going to be using logistic regression, which we'll get to in a bit. Okay, cool. Perfect. Right, and so this is all of our data, but we want to split this into our train and our test data, okay? Now remember I said before that we'd have some training data, and then we'd have some in-distribution test data, and also some out-of-distribution test data. So let's split this up, and again, these are probably some kind of familiar formulations that you've seen before, a very standard way of splitting our data. And we'll use this function here, and let's make a new line. And we're going to be splitting on x all. You can see up here, these are the sequences that we're putting in the arrays to split on, which we just defined up here using the make moons function. Okay, and then we want our test size. We could pick anything here really, but I'm going to pick 0.3. And then random state is going to be RNG again, and we will stratify on y all. Okay, cool. And then the final thing that we want in this section is our generate OOD data. Okay, perfect. And this is just going to be basically a separate Gaussian cluster. Okay. Gaussian is another word for normal. So your Gaussian distribution or your normal distribution. So we can do that with rng.normal. There we go. And we can put in where we want it to be on our axes. And I'm going to put 3.43. This is where we're centering it. And this is going to be our scale. You can see here the description. Oh, it's got even the mathematical description. The history. Let's see if it tells us what all of these do. It can give us the information that we need. There you go. So the scale is the standard deviation of the distribution. And this is how we center it, i.e. the mean. And if you're familiar with a normal distribution, the two parameters that you have are these two. And so these are the things that are going to decide the kind of shape of our blob, if you like. And we need actually one for each dimension because we're working in 2D data. So instead of just on like a number line like this, we're going to have more like a kind of circle or oval type shape. And let's pick the size of our data. I'm going to go for 120 by 2. Okay, perfect. And then let's just print shape summary. Okay, and we will put in here shapes. And let's have a couple of new lines. Copilot's predicting for me. This looks good to me. We might call that IND test and OOD test. And this is just going to be our training data. And we can delete that and delete that. Okay, let's give that a go. Okay, cool. So we've got our training data. We can see they're all in 2 dimensions, which is ideal. We've got 420 pieces of training data, 180 of in distribution, 120 of out of distribution. This is fine. We don't really care too much about like how many pieces of data we have. This is enough to demonstrate. So that's great. I'm going to save that and we run it and it's all gone well. So hopefully we are kind of at a good point here. Let's see. You're welcome from Algeria. That's super cool. This is one of the things I love about Global Hack Week is how international everything is. It's really cool to see people tuning in from all over the world. Cool. All right, I think we'll move on. I hope I haven't missed any questions. If I have, definitely just like ping me again. I do sometimes have a habit of moving too quickly, so let me know if you want me to slow down as well. But yeah, so let me double check again. Oh, we do have one. Okay, nearly caught up. That's okay. We can chill for a second. So we've got one question. I see here. Yep. What's random state and stratify? So this is basically just seeding our run. So it means that we can reproduce it. So if you were to do exactly this code, you should get exactly the same results. Now, this is not always true because of hardware, especially when you're running things on the GPU, which we're not today, but if you were, that can cause a lot of differences. So if you're doing deep learning, PyTorch is maybe something you're familiar with, you'll be probably aware of the fact that even if you set the seed the same, you can get different runs on different hardware and different results. But on your own device, if you run the same code 1,000,000 times with the same seed, you should get the same results as long as you've seeded everything correctly. So this is for reproducibility. Stratify basically just says we want our splits to be representative of the kind of distribution that we have across Y. And in this case, that's because of the half moon shape that we have. If it wasn't stratified correctly, we might have different distributions ending up in our in distribution test split, which is not what we wanted. We want it to be exactly kind of representative. Yeah. So we need to stratify. We obviously don't have to do that for the out of distribution test because it's out of distribution intentionally, like it's got a completely different distribution. So stratifying would be meaningless. Okay. Hopefully that answers your question. We've got another question here. I don't know, what should I do now? Can you explain? I have no idea. That's okay. No worries at all. So hopefully you've got yourself an IDE, like VS Code is what I'm using, right? This is just a place where you put your code. I would recommend opening up a new project. You can do that by going up here somewhere. I do it with commands, so I don't actually know. Yeah, if you clicked open folder, there you go. Click open folder. And then you can create a new folder and work from there. You can also do it in the command line with make a directory like this, and then you can cd into your directory. But VS Code has all of the kind of little buttons that you need if you're not too familiar with the terminal. And then once you're in, you'll need to write this code out, which we've kind of talked through over the last 10-15 minutes, and then hopefully run it, and you'll have some data. When you hover over scale, you get comprehensive description. Yes, so I'm actually not sure what I use. You mean like this, right? It will be one of my extensions. I can't actually remember. I have so many, and I set this up so long ago. It's none of those. It's none of these. It might be pylons. Not 100% sure. Might be pylons. It will be one of my extensions. I can find it later. Maybe we'll take a break halfway through, and I'll go on a hunt for you. It's probably pylons. I don't think anything else here would do that. That's the one that makes sense to me. So, yeah. There are like a whole bunch of bits and pieces that you can get like as extensions, which make it much nicer. I actually don't have too many, to be honest. I feel like there are lists online. If you Google like what are good extensions to have in VS Code for working in Python, there'll be like a whole load. Lots of mine you can see here are R. This is just like a formatting one, so if I open CSVs, it's not horrific to look at. You can see this linter for JavaScript, which is disabled because I hate working in JavaScript. Probably at much contradiction to many of the other coaches. And this does some code formatting for me. It could be this actually that does it. Maybe Prettier is one to try. I'm not actually 100% sure. Then I've got like a whole bunch of Jupyter extensions, bits and pieces, which, like, to be honest, I don't actually think do all that much, but there you go. So yeah, we are working in a Python notebook. For anyone who's like used to just like running scripts, this is like an exploratory file type which allows us to run just code segments at a time. We call these cells, and we can also make markdown bits which have like all sorts of nice formatting, right? Okay. So I'm hoping people are caught up. I'm going to keep moving until we get to the end of this section, and then once we're there, I will maybe push to GitHub, and then people can clone or fork or do whatever they want. Yeah, cool. Okay, I hope people are happy. The next thing that we need to do is visualize it, because visualizing our data is what we should always do because we are good scientists, and that is what scientists do. I know many of you here are probably like, oh, I'm not a scientist, I'm an engineer. But actually, today, when we're working with data, we are scientists. I'm going to just define some new variables because it's going to be easier for us to plot with these. I don't want to accidentally like muck with our, oh, what have I done? Should this just be X test? Yeah, let's actually rename this to oh, we didn't need that. And yeah, I'm gonna make these slightly more descriptive. I know that's breaking it down here, but because we also have this data, which is actually our test data as well, technically. So I'm gonna rerun that. Okay, we've pulled these out. And now let's make some plots. So this is classic matplotlib, and we can do plot.subplots. And then we're going to do several different plots. We're going to first plot our train data. Let's see, has this pulled it in correctly? I'm just having a little look at this. This looks good to me. I don't want this really. Yep. And I'm going to make them, oh, we've already got alpha in the back. Okay, I'm going to make them slightly more solid than that. So alpha, for anyone who doesn't know, controls the transparency of your little points. And we already have a label. So I think actually I'm kind of happy here. Yeah. For anyone who's not familiar with this, maybe will it put it up? No, sad times. I'm sure there's some way of getting all of the like little tips for those, but I don't know off the top of my head. So this is all going for now. And we're going to do the same for our training data, and then we can also do the same for our out of distribution data. And we're going to just change this here and change this here to be a little bit more opaque. The reason that we want these to be slightly more transparent is because they're going to overlap because they're in the same distribution. Okay, and I'm fairly happy with that. So now we need to do the standard matplotlib stuff. We're going to set a title. We're going to go in distribution or IMD versus out of distribution OOD data. Cool. And let's set some labels. So feature 1, yeah, we can call it that. I was going to call it X1, but like fundamentally the same thing. This is feature 2. Sure, we're going to have the legend, and then we're going to hopefully show our plot. Now, hopefully this all makes sense. This is just some standard matplotlib stuff. If you're not familiar with matplotlib, you should pick it up pretty quickly. I've typoed, so that wouldn't help. And then we'll run it again. Okay, perfect. And maybe you're going to give it a second before moving on too far. Let me know if you've got any questions. Looks like we don't have any questions so far. So hopefully we've got to this point, right? And this is what I was talking about earlier, right? So you can see here probably that we've got these 2 half moons, okay? We've got one here like this. We've got one here like this. And that's how we generated our data to be. We had to make moons, okay? All right. And this is our test data in orange and our training data in blue. And you can see that they follow exactly the same distribution. We've got this one moon here and this other moon here, and they kind of interlock, right? And then we've got our other test data. This is our out of distribution data. You can see it's all the way off over here. Its distribution is completely different. It's going to have a different mean. It's going to have a different, well, it's going to have a standard deviation, which this will have, but it's not going to be the same, right? And the distribution of this is not this funny little moon distribution. It's a Gaussian, a normal distribution, that bell curve. And you can probably kind of get that if you imagine looking down at this in one dimension. You can imagine the density here is thicker. That's where our bell goes up and down. And you can also do it the other way, or any way really, any way that you cut it. Cool. Okay. Neat. Right. Perfect. Okay. I think we can move on now. Hopefully we understand what out of distribution data is now. And also we can have a visual interpretation of that and how we want our model to distinguish between them. Yeah. Cool. Okay. So what we want to do is we want to say, if our model is fed in this data after we've trained it on this data, it should have a lot of uncertainty, but some models won't. And we'll see that pretty quickly. Cool. Okay, so what I want to do is just for some like good practice, let's save these various bits and pieces that we've built as artifacts. And this is just going to be a folder. So we're going to import some libraries that help us do this, and we will make a directory. I'm going to call it artifacts. Ooh. And yeah, we'll say exist OK true, which means that if it exists, just leave it alone. Otherwise, make a new one. And we'll save our arrays. So we're going to save our data here. Cool. And I actually don't think I want to save them as pickle files. Yeah, let's save them as NPy. Okay. And hopefully Copilot, yeah, Copilot is doing a great job for me. You can type this out. Or if you kind of can't keep up, that's all right. I'll pause in a minute. But we can see that we've saved all of our different data. So we've got our training data, we've got our in-distribution test data, and we've got our out-of-distribution test data. And we're just kind of saving this so that it's convenient for us later. And also, if we do build a little demo dashboard, this is going to be super useful for us. So I'm also going to save it as a CSV, and this is going to be for easy viewing, yeah, sure, and also for Streamlit demos, yeah, sure, okay, later if we get to it. Perfect. Okay, and this is going to be a whole load of just manipulating our data a bit, and this looks good. I'm actually going to call this x1, x2 because it's a little bit more convenient shorthand for me to type out later. We're going to say, yeah, 2 CSV. Oh, the kernel crashed. I don't think we ran any code, so that's a bit sad. What I'm going to do is I'm going to restart my kernel. Hopefully none of you will have this. And then I'm going to rerun all of the cells above. Okay, perfect. And now that we've got this, I want to just make 3 copies of it and change them. So this is going to be X distribution test, Y. Normally Copilot's jumped in by this point and tried to fix everything for me. We actually don't need this because we've just got one array here. And it's X out of distribution. Okay, perfect. And then we can print like saved data to artifacts folder. Perfect. And if we run that, hopefully it won't cry. Okay, of course, we don't have a label here on this data. In these, we have our Y value, which is actually the moon. So if it's in this moon, it's going to have a different Y value to this moon. And we don't have that here because it's just a blob, right? So these are kind of our 2 classes. The Y value is indicating our 2 classes. And that's actually going to be what we're going to try and predict later. Like predicting whether it's a cat or a dog, we're actually going to predict whether it's in this moon or this moon. Okay, cool. So if we run that again, it's going to save our data, and you can see that we've got let's fix this. Oh no, we don't want that. We want test data, and then we want test. We can just call this out of distribution data. It's not really test data. It kind of is. But okay, perfect. So that ran correctly. We've got all of our different bits and pieces here. It's not going to be happy opening them. As I mentioned earlier, I've got a nice rainbow CSV formatter, which makes this nice and readable. So we can see x1 and x2 here. Or if we go to these, we've got x1, x2, and y, which is just a Boolean saying whether it's in class 1 or class 0. Cool. Okay. Yes, hello. I can see the chat. I've just spotted your messages. I don't check it like 24/7, so sometimes it'll take me a minute to pop in. Let me see. So you've recently got to know about MLH and you'd love to become a member of the community. Well, don't worry, you're in the right place. Hopefully you're in the Discord. If you're not in the Discord, I think the link is discord.gg/MLH MLH. Yeah, it is. I've accidentally just opened my Discord. Now I can't see anything. Okay, you're not in the Discord, no worries at all. So if you head along to this link in the chat, I would recommend heading along there, and hopefully all of your questions should be answered. It's got some nice introductory stuff on how to create an account with MyMLH, which allows you to chat in all of the channels. And it's just a really great place to be part of the community. What you're in right now is a Global Hack Week stream, and so we're going to keep on with that in a second, but we're going to be building things together, and that happens at all of the Global Hack Week streams. And that's once a month. We have a Global Hack Week. So this month it is data, and we're having a really good time. We're having a really good time. So if you haven't already, you can pull up VS Code or something like that and code along with me. Yeah, no problem at all. Hopefully it should all be like fairly intuitive when you hop into the Discord, but I would also recommend checking out the MLH website. It's got FAQ sections and stuff which should answer most of your questions. In particular, check out the schedule on Global Hack Week on the Global Hack Week website. You can find that here. And if you head along to what's called Today in Global Hack Week, there'll be someone who can help you out with any questions. I think today it will be me, actually, and that's in a couple of hours from now. So you can head along to that stream too. Okay, right, let's see what we've got. So we said earlier that if we check the mean and standard deviation of these, they would be different, noticeably different. Let's do that. Let's actually just verify, let's do a little sanity check that our data is as we expected. Okay, and we're gonna pull in some parameters. We're gonna make a custom function just to summarize our data for this particular use case. And we're going to get the mean out, so we'll call that M, and we'll do x.mean, because this is just a NumPy array, it's not inconvenient, and we'll just do it on the first axis. And we'll get the standard deviation in the same way. Okay, perfect. Right, and then if we print, we'll do an F string. These allow us to make nicely formatted outputs. And I'm gonna just, yeah, that's nice. So you can fiddle about with the formatting here, but the most important thing is that we're going to just print out the name that we get in and also the means and standard deviations. Okay, and now if we run our very simple function on our training data and also our in-distribution test data and also our out-of-distribution data, we get a nice formatted response. So we can see this is our train data, this is what we put in first, this is our in-distribution test data and our out-of-distribution test data. And we can see that the mean for these very similar across both across both x1 and x2. So these are our x1 and x2 values up here. So the mean is 0.5 by 0.27. So 0.5 by 0.27, that seems about right. This is about the mean. And yeah, we can see that that's about 0.27 there, 0.5 here. That makes perfect sense. The standard deviations, so we can see that it is wider in the x-axis than it is in the, well, the x2 axis, right? So it should be wider along the horizontal than it is tall across the vertical. And we can see that too. It's definitely wider than it is tall. And then let's have a look at our OOD data. Okay, wow. So the mean is way higher, 3.43. So we can see that up here. And the standard deviations are a little bit tighter. You can see it's less wide. So this is good. This is what we expected to see. And we're pretty happy with this. Okay, so I might initialize a repository here and make a get ignore because it's currently tracking our, there we go. So I've just added our virtual environment folder to our get ignore, and hopefully hopefully there we go. Yeah. Much better, much better. I might actually also ignore the artifacts folder because I don't really want to commit data. We could, but I don't really want to. We kind of just want the code. I'm just going to call this initial commit because I'm feeling lazy, and I want to publish this branch, and I'll publish it publicly. Perfect. And so anyone who wants to can follow along. They'll be able to see all of the code that they want to. And so the link for that is just in the chat now. There you go. So anyone who's fallen a bit behind, do not worry, you can catch up immediately. Great. Okay, we had another question. Each week we'll have a new stream on new topics. Not quite. So every month we have a global hack week. And so 1 week within the month, we have a new topic and new streams. So this month, for example, it is on data. I think next month, so October, it's on open source. November, it's on APIs. So yeah, there are themed weeks, and yeah, you can pop into all of the different streams. You can check out the schedule that I linked and find out more information. But for now, we're coding. So if you have any questions about that, I do recommend going to the Discord. All right, so section 1 is done. This is great. This is great. Now let's move on to section 2, and we're going to build a bit of a. We're going to build a baseline classifier. So we're going to classify into these. Where did I have them? I had them in here, didn't I? Yeah, into whether they're in the 0th moon or the 1st moon, basically. And that will become pretty clear in a minute. Build a baseline classifier, and this is going to be logistic regression. And see why it's overconfident on OOD. Right, this is not what we want. This is basically an example of something that breaks. Okay, perfect. Right, and okay. So actually, maybe I'll put a little bit more information in here. So, okay, what we do here is for logistic regression. The way that it works, it's kind of like linear regression. So it's a pretty simple model, but it computes a linear score, which basically describes how likely it is for a data point to fit into a class. And then what we do is we pass it through a let's sigmoid. And if I highlight this, can we make it bold? No, formatting doesn't work here. Okay. We will just type out the markdown ourselves. That's italics. We can go bold. Okay, and we pass it through a sigmoid. This is a function, and it's just an S-shaped curve. If you want to see what it looks like, you can Google it, but it's just an S, basically. And what this does, the sigmoid translates our score into a probability. If the score is near 1 or no, if the score is very positive or very negative, the sigmoid saturates near 1 or 0, i.e. high confidence. So the thing to notice here, objective, notice that our model will have high confidence even on data that's far from the training distribution. This is what we call warning. Overconfidence on unfamiliar inputs. This is what we're going to be scared of, basically. Okay, So that's a little summary of logistic regression and potentially what we're looking to test. Okay. Perfect. Right. And for the sake of reproducibility, we can pull in our data. Let's make a function that loads it from artifacts. This is going to be nice. This is like a good way of engineering well. And I'm going to speed up slightly now that we've got a GitHub. I'm going to speed up slightly and I'll just commit and push to it semi-regularly so you can pull and follow along. Cool. Okay. I'm going to, from pathlib, import path. This is part of the reason that we're doing this is that so that if someone loads up this notebook and they haven't run all of this, but they have the data, they can just import it in. And so this is our artifacts path. And let's also set the random state again in case someone missed that. And we're going to make a function. We're going to call it load data. And we're going to say if yeah, perfect. If we see our training data in our artifacts folder, let's load it all in. And then we will just do a print loaded data from artifacts. Perfect. And then if not, we will say we could, oh yeah, we could generate it. I think I kind of would just want to raise an exception. Yeah. Perfect, because I can't really be bothered to load up to reproduce all of the code that we had up there. If you wanted to, you could like have this code here and you could pop it in down here so that if someone hasn't loaded the data, it loads it automatically, but like that's a little bit overkill. Okay, and so we're going to do this. Perfect, thank you, Copilot. And we can just print a summary again. Perfect, this is the summary that we had before. So let's run that and we can see that it's loaded it all fine. Yep, this is exactly the same data. It's exactly as expected. We can see that it's loaded it well. So this is good for us. So let's train a super simple, super fast classifier. And we're going to need not that, actually. So we're going to need make pipeline, which allows us to make a training pipeline. And then we need pre-processing, and we need standard scalar. And let's also pull in a linear model, and we're going to want logistic regression. So we don't have to code up this ourselves. Fortunately for us, this wonderful library called scikit-learn will do it all for us. Okay, and classifier. We're going to say make pipeline, not with a space, make pipeline, and we want to scale our data and then run the linear regression on it. Okay, so this puts our features on comparable scales, and this is our logistic regression model. Okay, this is really CPU friendly, by the way, so don't worry if you've got like a bit of a slow laptop, it should still be fine. And so now what we're going to do is going to fit our model onto our data. And we're going to fit it on the training data. Okay, this is important. We're not fitting it on the test data. That would be bad. Don't do that. And then maybe we'll just do like a little print out saying train a model. Yeah, fine. Okay, so the model is trained. This is good. As you can see, it's like super fast. And let's just do like a super quick evaluation on how it performs on our in-distribution test set. Okay, so accuracy is probably what we're going to be looking at most because it's a classifier. So seeing how many data points are correctly fitted into the right class in the test set. Oh, got the hiccups. Okay, I'm good. I'm good. Okay, right. And let's import some useful bits and pieces. So accuracy score is what I just said would be useful. And we also, yeah, let's have classification report and also confusion matrix. A confusion matrix is a matrix, so like imagine a table, which basically just describes where our model has correctly or incorrectly allocated data points when it's classified them. We actually already have pandas imported. I was going to import it again, but we don't need to. If we were running all of these sections as separate files or notebooks, you would want to do that, of course. And this is part of the reason that I've set out our code in this way, because if you wanted to make this modular, you could. And that would maybe be a good thing to do if you were building a dashboard. Looking at the time, I'm not sure we'll get that far, but we can give it a go. Okay, and now what we want to do is we want to predict on our in-distribution data. And so to do that, we're going to call our classifier. I'm going to say, please predict on our in-distribution test data. Okay, perfect. And then we're going to get the accuracy score, and we just basically say, these are the ones that we predicted. These are the ones that are actually true, i.e. our ground truth. How many are right? Okay, and we can just print this, test accuracy, perfect. We can also get out a classification report super easily. I might delete that and get it to put in okay, yeah, there we go. So I've just typed that out so we get a bit of a clearer print out. This is going to summarize a whole bunch of different bits and pieces for us. I don't really want to go into too much detail on like the metrics that we use, but it's just going to get us a bit of an overview, which is good to do. And yeah, we can print the confusion matrix. This might print weirdly. It's okay. It's not great. Yeah, okay. Perfect. So we can see that our accuracy is about 87%. That's pretty good. This is all kind of as expected. I don't really, like I said, I don't want to get too much into the detail here, but 87% accuracy is pretty interpretable, makes a lot of sense. These are the ones where we've predicted incorrectly. Again, like I have kind of little care about how good this model is at actually classifying on the in-distribution data. All we need to see is that, okay, it performs reasonably well. There's clearly some amount of data which is not like perfectly classifying. And as a reminder, this is going to be our aleatoric data. So where it's noisy or close to perhaps some boundary. And we can visualize that really clearly by looking at this and saying, okay, if I've got a piece of data that's like here, you can see how it could be part of, or like even here, right? Here is probably the clearest example. You can see how it could be part of here or here, right? And actually a logistic regressor, the model that we've built, the logistic regression, is a linear model. So it has just a score which it assigns. And you can imagine that as a line, and it's just a straight line, okay? So if it's trying to split these moons up, it's probably got a line like down here. But like that's not perfect, right? Because these are probably part of this moon, and these are probably part of this moon. So there's going to be noisy bits. And this is the kind of the aleatoric. I mean, to some extent, it's not aleatoric. Like some down here are going to be like, that's going to be aleatoric uncertainty. But the noise here is going to confuse our model because it's not like a particularly sophisticated or closely fitting model. It's a decent enough model though. And very common, often what you want is something simple. So let's build a decision heat map. And this is going to be a really nice plot. And what we're going to want to do is we're going to have this basically here, but we're going to have the background shaded according to the decision that the model has made on whether to put it in this class or this class, okay? And I think it will become a lot clearer when you see it. Okay, so we want to, first of all, build our bounds for our data. And this is going to be, yeah, a vertical stack of our training data, but also not this, our out of distribution data, because this is higher up, right? And so we want to make sure that we're bounding our heat map correctly. And as a reminder, the heat map is just something that's going to represent the decisions that our model has made and visualize it for us. Okay, and let's add some padding to this. And so we're going to grab out our minimum X value and our maximum X value from our bounds. This is kind of like we're stacking up these on top of each other, and we're saying, right, let's make sure that our axes include this data. So this is a little bit finicky, but we're also going to do the same thing for y min and max, because remember that our training data is two-dimensional, so it's got x1 and x2, which we're assigning x1 to our x-axis horizontally, and we're representing x2 vertically on our y-axis. Great. Okay, and so now we want to have a grid of points across this rectangle that we've made, basically. This is just a rectangle. Okay, so I'm gonna maybe add a little comment up here just so we're super clear. Construct bounds that include train and OOD data. Perfect. And so we want a grid of points across this rectangle. And so we will say, yep, we want a mesh grid. So this is NumPy mesh grid, and we're going to use this linspace function, which basically just produces kind of like an array across a range for us, and we'll accept that. Let's make it 500, a bit more resolution. Okay, these are the number of points that we are putting on this linear space. Okay, and then we are going to make that into a grid. Perfect. Okay, don't get too kind of caught up in the details of the syntax and semantics here if you're not too familiar with NumPy. This might be a bit weird to you, but it's okay. Okay. Perfect. Right. Okay. And now what I want to do is I want to get the probabilities out. So let's make a new comment here. Predict probability of class 1, so where y is equal to 1, for each point in the grid. Okay, and the reason that we made this grid is so that we can do this. So we're going to get out the probabilities across basically the whole backdrop of our plot. And this is going to allow us to, okay, predicting the probabilities, visualize it with a heat map. So we're basically building the data, the information to do that. And we're going to make sure that we deal with our dimensions correctly. And we're going to grab out the shape of our x's, because obviously this is our our dimension. Cool. Okay. What I'm gonna say, Gamerash, is open a support ticket on the Discord. You should be able to access support tickets, or come back at Today in Global Hack Week and I'll help you there. That's in about an hour and a half, hour and 45 minutes. I want to make sure that we kind of get on with the workshop. If you're having issues with this, the Discord is the best place to go. And once you've verified, you should be able to. Yeah, you got access. Perfect. Okay, cool, cool, cool. All right. Okay, so hopefully we've got some probabilities out here. Maybe we'll just print probabilities here just to check that we've got some. Okay, this looks horrific to us, but let's check the shape of it. And we can see it's 500 by 500. Perfect. Okay, 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 okay. That is good. That is good for us. If you're interested as well, we could grab the shapes of, yeah, all of these. So should be nice and intuitive, but this is the shape for our x's, which is ideal because that's what we need, because those are our features. Okay, and now we need to make a figure. So let's actually do the plotting. Okay, and so we need to make plot the figure, and we'll set the figure size. 8 and 6 is fine to me, I think. Get my fingers on the right buttons on the keyboard, and we want to add a contour. And this is going to be our background heat map. Okay, And let's set, this is all kind of okay. I want to make more levels just for the sake of clarity. And we'll give that a run. Okay, and so we can see what we've made, which is really good. This is the line. And we want the rest of our data points on here. So let's fix this up a bit. But this is looking good so far. What we really want is to make this a bit more polished now. Okay, so we're going to make a line at our decision boundary. This is exactly where the probability is 0.5, so it's not really sure which is which side. This is kind of the least certain place, if you like, because, of course, if its probability is very high or very low, it's very confident that it's either in class 1 or class 0. Okay, and we're going to set that as our label for this nice little line. And if we plot that again, lovely. Are getting an error. Quad contour set has no attributes collections. It's possible that this is like a version thing. I'm gonna let's have a little think what's going on here. Do some debugging live for you all. Okay. So okay, let's redo this in a different way. First of all, I forgot that we need a color bar. So let's add in a color bar first. We'll come back to that. Very interesting. Okay. Yeah, let's make a color bar. So we're going to call our color bar cbar, and we're going to say plot.colorbar, and we're going to call in contour, and we're going to actually set this to be equal to contour. So this is so that we can pull out a color bar on our background. And yeah, we've got a color bar. Perfect. Okay. And then let's set the label for this to the probability, which we just denote as P brackets of class equals 1. And that will be enough. I don't really want to rotate it or do anything else here. There we go. Nice. Okay. And now, let's try and build this line down the middle again. We want a line just going dead through this 0.5 decision boundary. And I think we still want a contour, but we want to put a label on the contour, and we were having issues with that. That was the problem. So let's call it in like this, line stars. But then I think we should be able to set line. Let's set line widths as well, but let's put it as 2, so it's a bit thicker. And then I think we should be able to set a label here, right? Yeah, label equals decision boundary. Okay, we don't have a label. Honestly, label's not required. We know what that is. This is just for our sake of visualizing the data anyway. So I'm not going to faff about with this. Let's plot our data. So we will put it in. I'm actually going to paste this in from my notes because this is basically the same code that we had up here. Slightly different, to be super clear, but it is basically the same. So if we plot this now, perfect. Okay, great. So this key is actually not a very good key, but it's maybe a lot of a faff to fix it. What we've got is in the circles, we've got our training data. And so you can see those circles all around here and circles all around here. And then the triangles here are our in-distribution test data. And you can see them all around here as well as all around here. And what we've done is we've set the color according to whether it's in class 1 or class 0. Actually, is that right? Yeah. No, wait, sorry. Class 0 and class 1. Yes. Because the probability that it's class 1 gets higher this way. So this is class 1, this is class 0. And you can see here that there's some... Can I zoom in on this? Don't know if I've got a zoom in button here. Yeah, okay, I can. Perfect. So you can see here that we've got a very... it's just a linear model, basically, and it's classifying, splitting it across these using that sigmoid function. And oh dear, it's not doing it perfectly, but this is okay. This is kind of not what we really care about. It's a very simple model doing a very simple thing. But you can see it gets very uncertain on this line, and that's kind of understandable. This bar represents the probability, the confidence that we have that the point is in the right class. And up here, this is our out of distribution test data. And you can see here that it's actually in the most confident bracket that we've got. I mean, it's like basically the probability that it's in class 1, it's like it thinks there's a 0% chance that it's in class 1, basically. It thinks almost certainly this is class 0. And actually, it's not in either class. And so this would very confidently, this model would very, very confidently predict that all of these are in class 0 without flagging it to us. We would have, the probability would be very high. And that's really bad, really, really bad. And we can show that in another way as well. And again, I'm just wary of time. I'm just going to copy and paste in some code. I don't want to generate anything though. No. Okay, perfect. And this is that probability kind of visualized. So the predicted confidence, i.e. the maximum class probability, the probability that it's in each class, that we pick the most likely one, right? So here, it's the probability that it's in class 0. And we can see here that our out of distribution test data is in the orange, and it's extremely high in probability, extremely, extremely high. Whereas our in distribution data is like a little bit more normal, right? We kind of see that we've got a bit of a bump here. This is good, but we can see there's a bunch of it which is like falling in here, right? So this is this range, this bit here, where it's just not certain, i.e. this range. Actually, all the way up till here, all the way down till here. It's mirrored. And so this is very, very bad because this model is extremely confident on data which it's never seen before. That's really not what we want. And so this is the kind of idea that we're dealing with. Okay, we want to get some predictive uncertainty, which is actually dealing with this. Okay, and that's basically the crux of it. Yeah. Okay, so let's save this model, just like we've been saving all of the other bits and pieces. We've actually already imported OS. We could import OS and JobLib again, but we've already imported them. And I want to, we already know that we've got this directory. We could just do this again. It exists, so we're not going to overwrite it. And let's dump in our model, and we will save it as a, we'll save it logistic regression baseline, and I want to save it as a pickle here. This is just like a way of compressing like a Python object, basically. And then we'll just print that we've saved it. Yeah, perfect. Okay, so if we run that, right, we've saved our model. So this is basically the premise of section 2. Remember, our objective was to identify that our model has high confidence, even on data that's far from the distribution. And huzzah, that's what we've seen. Great. Okay, so we also saw in a very, very obvious way here, crazy how overconfident it is. And that's not great. So let's commit this, added section 2 contents, and we'll commit, and I'll sync the changes up to our remote. And so if any of you want to pull those down, you can do so. Okay, perfect. So what can we do about it? Well, section 3. Let me check, see if we've got any questions. I haven't seen any for a bit. Just taking a drink of water as well. Keep hydrated, hackers, keep hydrated. I can see that we don't have any questions. That's great. Let me know if you do have any thoughts. Otherwise, we will keep moving on. Okay. And so, how much time do we have? We've got about 30 minutes. I'm going to say, actually, so one of the things which we could do, and maybe we'll skip over section 3, or maybe I'll just paste in the code for this, actually. Yeah, let's paste in the code for this. We could have an idea, right? And we could say, like, okay, what if we try and calibrate our uncertainty? What if this here is just not, it's because we've just not calibrated it. Maybe you're just being unfair, Quinn. And there are some bits and pieces that we can do to kind of try and fix this a little bit. We'll have a think about that now. But first, let's have a little recap, because I think there are some ideas that we've spoken about. So the first thing that I want to address is confidence. Here, at least, is the model's own predicted probability for its chosen class. And predictive, oh, let's get that in there correctly. Uncertainty is the idea of how unsure the model is about the label. Okay. So these are subtly different, but maybe the point to make here is that a logistic model's confidence comes from the sigmoid of a linear score, not from model ignorance. It has no concept of predictive uncertainty, no concept at all. Okay, so can be very overconfident. This is basically just what we see. Okay, and we could pull in the model again, but we've already got it loaded, so I won't do that. There are some plots that we can make here, and I'm just going to paste in some code, and you just don't have to worry about this. There we go. So you can see here that this is like a pretty poorly calibrated model. I won't go into too much detail again on these. These are just kind of like visualizations for us to see. This is both on our in-distribution data. We can see even then, like, it's not super confident, especially like around this like decision boundary here. It gets pretty confused. You can see that, like, if it's just splitting it off, all of these are going to be wrong, all of these are going to be wrong, some of these are going to be wrong. So it's not great, but we can see it's okay. And we could think, well, maybe if we calibrate it a bit better, we could produce something a bit, more reliable. And we can do this with something called temperature scaling. And so what we do here is we keep the model the same, the scores are exactly the same, but we kind of soften or sharpen these probabilities. And we do this with a parameter called t, and we apply it to the logit. And the logit is just the score that we have before it goes into the sigmoid. You've probably heard about logits when talking about neural networks, but they also exist here, especially for this particular model. Okay, and we could have a little bit of a play to see if we can minimize what's called the negative log likelihood. This is something that's commented here. We actually calculated it down here. This is pretty high. It's not very good at all. So we could be like, okay, well, Quinn, maybe you just built a bad model. Maybe we could just try and calibrate this on like a validation data split. And this is like some slightly hacky code that does this. And it works. It's picked a temperature of 1.258. And so if the temperature was 1, it would stay exactly the same. If it was less than 1, the probabilities would get sharper, so more extreme. But in this case, it's above 1, which means that we're kind of softening our probabilities. We're making it less extreme. We've recalibrated it now. So again, like, I'm not expecting anyone to type this code out, but we could check these again, these little plots. And again, I don't want to get too much into the detail here. It's not much better, basically, is my point. We can like improve our models slightly. This is showing that it's kind of like not as extremely confident, right? You can see how we've kind of softened these confidence kind of calculations, the predictive probabilities, but it's not much better. Actually, our negative log likelihood has gone up, which is not good. Basically, my point is that like this is not really going to fix the problem, because the issue is not really the calibration of the model. It's the fact that it doesn't even look at this idea of model ignorance. It has no idea like that this is different data. It has no concept that this data is distributionally different to this data. It doesn't even come into its little head, right? And I'm anthropomorphizing this model a lot more than it should be, but that's the way it is. That's the way it is. So basically, this temperature scaling idea, it only focuses on the in-distribution data anyway, and it doesn't really fix anything. It shrinks the extremes a bit, so you can see here that after temperature scaling, we're less kind of extremely confident at the top end. This would have an effect on our out-of-distribution data, you can see here. So the median confidence has gone down, right? It is less confident on out-of-distribution data, but like by the tiniest amount, like such a small, I mean, look, the scale here is ridiculous. So this doesn't really work, and we need a new model, basically. We need something that has this concept of predictive uncertainty. And I'm going to commit this again. Let me save it. Section added, section 3, and we'll commit and sync that up for you all. So yeah, like I said, don't worry about like getting into the ins and outs of all of this. You can Google this, and like some of these metrics are interesting. But the point is that we can't really fix it. We need a model that has this idea of predictive uncertainty, which this one does not. And so let's get on to section 4. This is where we get properly exciting, and we are looking at Bayesian logistic regression. And then we're going to have this idea of what's called a posterior predictive. Okay. So our goal is to train this Bayesian logistic regression model. Maybe we'll abbreviate it to BLR. And the premise is that this will stay cautious. We'll put that in quotes. Stay cautious on unfamiliar, i.e. OOD, inputs. And yeah, it will help us deal with epistemic uncertainty, i.e. it will maintain uncertainty for data that is different to what it's seen already. Okay. I can see we've got a question in here. Okay, I copied the iris logistic regression example and tried to run it step by step. Previous execution ended unsuccessfully. I checked the libraries and started running the code cell by cell. Now I understand better how to debug when something doesn't work. That's really cool. That's really cool. I'm super glad that you've managed to get it working. I think it is very satisfying when you kind of debug something, especially by yourself for the first time, and get to code that runs. Especially like when you get like, I think plots like this one, I think is very satisfying. So we're going to get some really nice plots in the next we got about 20 minutes left, and we're going to get to a really nice point here as well. So the way that this works, very loosely, okay, is logistic regression picks one, I'm going to put this in capital letters, one best set of weights, okay? And what BLR does, Bayesian logistic regression, is it keeps a distribution. Remember, a distribution is just like a curve, describing the way that our data is kind of positioned, right? So like people's heights, which might be centered around the average height. Most people are near the average height, and very few people are really tall or really short, right? We've got a distribution, some little line that describes how our data is laid out. BLR is going to keep a distribution of plausible weights. So instead of just being like, these are the weights that are true and they are always true and they are great, it's going to have like some idea of like, we've got a bunch of different models and we kind of aggregated them a little bit. That would be an ensemble. This is not exactly that, but it does keep a distribution, this kind of representation of different weights that perform on this training data. Okay, so when, actually you can just do like, when data inputs look unfamiliar, many weight settings are plausible, right? And averaging predictions gives less extreme probabilities. When we say that, we just mean closer to 0.5, right? 0.5 is like, I don't know. Especially when you've got two classes, that's just like, it's a coin toss. I don't know. Okay. And we also get higher spread across samples. And this is epistemic uncertainty. Hooray. Okay, so we can see, hopefully, that we've got this model, and we've got maybe like a very high level intuitive conceptual idea of how it's going to work. And we're not going to implement it by ourselves. We're going to use a library again. And the code that we're going to use to do this is going to be like potentially a little confusing, but that's okay. We will get through it. And I'm going to set some constants first because it's good to do. This is our grid resolution. These are our posterior samples. If you're not familiar with like Bayesian stats, this is going to be a little bit confusing to you. I think I went over an intro to this in one of my workshops. Yeah, I think I did a workshop called Decision Making with Stats. And if you want to learn a little bit more, let me just double check that I actually did go over. Yeah, I did. So I went in like a lot more detail about like what Bayesian models are. And I don't really want to go through all of it right now because we probably just don't have time, unfortunately. But what I am going to do is I'm going to find decision making with statistics. I'm going to see if I can find it on the MLH YouTube for you and link you all to it now. Feel free to take this point as like a bit of a breather. I know we've gone like quite quickly through a lot of like theory heavy stuff. So maybe grab yourself like a drink of water, a snack maybe. Yeah, perfect. So this is the stream that I would recommend. I'm going to click share. In this one, I went over it in more detail. And it's probably like a good, I mean, it's 2 hours long, so similar length to this workshop, but like it goes into a little bit more depth. But the rough premise of Bayesian statistics is that you have this prior, which is a distribution, just like we've been talking about. This is a distribution, for example, by the way, of like our data. And like, you know, any like histogram really is a distribution. And we update it using the data and we say, okay, based on the distribution that we had before, what we expected to see, how likely was our data under that? And then you produce this posterior distribution. And when we're doing Bayesian modeling, what we often do is we'll take a bunch of different samples from this kind of posterior, and that will allow us to produce our predictions and so on more accurately. So perfect. Okay, so I'm now going to define pad. This is just our margin around our data when we're plotting it. Cool. If you don't like fully understand in your head like how Bayesian modeling works, that is okay. We will it will hopefully kind of like make sense as we kind of go through. But if not, like I do recommend like learning about this. This is like quite a complicated area of stats, and so if you're new to statistics, this is like a really big thing that you're doing. And the point is that these models are really good, and we're going to demonstrate that they're really good. So cool. Okay. I just want to make sure that, so when I was prepping for this workshop, this is like a little sneak peek. I had lots of issues because when we are sampling, we deal with like lots of different dimensions, and the way that I was like processing my features was like getting really complicated, and it was breaking lots of things. And so I just want to make sure that I am using the right code, because otherwise things will break. Things will break, and that will be sad. Okay. Actually, yeah, this is fine. This is fine for now. What we're going to do is we're going to make this function, and what it is it's producing a predictor that is bound to the same preprocessor. So when we preprocess our data, we want to make sure that our predictor is using the same preprocessing steps. Otherwise, it will not work. It will just throw errors and all sorts of things. Now, when we use a library like scikit-learn, which we've used like a whole bunch of times here and miles up, it handles lots of this for us. Because we're using a Bayesian model, it's not actually built into scikit-learn, so we're going to have to do some of this ourselves. In theory, like the library that I'm using should kind of make it easier, but it, in my experience, isn't always easier. This is one of the cases where I would be arguing that R is a really good language to learn, because R is built for this kind of thing. Okay, and so we're going to build this function that, yeah, will we can actually just set the seed to seed. What was I saying? Oh yeah, that will make sure that when we build our model and fit it, it actually kind of uses the same preprocessing steps as it does in the predictor. So these are our posterior samples. We can set that to posterior samples. Great. Okay. And what I'm going to do, again, in the interest of time, oh, hiccups again. My apologies, is paste in this function and give you a very high level overview of it. This function can take a little bit of time to run as well. In the interest of time, let's get it going. So as you can see, we are doing the usual stuff, importing and doing our setup. And then we're building this scalar. And we want to make sure that it only has these two features. This is like an issue that I had in the past. You can see my capital letters getting like slightly grumpy here. And we've got some printouts here that are going to check this shape. Because remember, we have x1 and x2, right? These are just transformations and checking that our input into the model is the right shape, i.e. we've got the right dimensions. If we had 3 features, we'd expect 3 and so on, right? Obviously, we have 2 because it's easier to visualize. We can only really make pictures in 2D. We can do 3D. 4D is like no. So, and then this is the syntax that we're using in this module. And I would recommend Googling it, but it basically abstracts away all of the nasty stuff that we'd otherwise have to do. And our priors here are normal distributions. So this is just this bell curve, really, really simple. And we are going to center them on our data and pull all of this through. Okay, and then this is where we fit this model. And in theory, it should use this progress bar. I think it actually breaks on my Python notebook. For whatever reason, I'm not actually 100% sure. Again, like something like R and RStudio are kind of built for this, so I would recommend getting familiar with those. And then we're going to get our posterior dimensions out and just check that they fit, that they have the right shapes, because if they don't, it's problematic. Okay, and that's kind of the crux of it. So if we had like a feature mismatch, we've also got some handling in here for it, but hopefully we won't see that. So I'm going to run this, which is just defining the function. And then we're going to actually fit our model and do the prediction. Okay, and so all the way throughout here, BLR, by the way, is just standing for our Bayesian logistic regressor or regression model. Okay, and This is fine. I don't really care about all of these errors. Like, I don't know. We could install IPy-widgets. I think we should have nice printouts here with like a progress bar and stuff. Like, it's probably just like some weird setup thing that I've got going on. But this will take about 4 minutes to run, I'm going to hope. And so we'll leave that running while we write the next set of code. Okay, and I'm going to paste in two really complicated looking functions, which I don't really want you to pay attention to, but I might even just minimize these immediately. I'm going to set that to run. What this is doing is it's checking that our posterior matrices, i.e., the way that we're processing our multi-dimensional data, because we've got x1 and x2, have the right dimensions, and if not, fixes them. Again, this is because of like errors that I had earlier, and like I really would recommend using R for this exact reason. Like it's not ideal. Okay, so this is the kind of like processing that we do afterwards. This is getting our predictive probabilities out, just like we did up here, wherever it was. Can't actually remember now. I think it was in here, wasn't it? Yeah, here. So we're getting the probabilities of each class. And here, it's not going to be ignorant to out of distribution data because it's got this posterior distribution over the model weights. Okay, great. So you can see here we do like this processing, and we do a shape check because again, like I was having some issues. In this case, we are using the same preprocessor because it's built up here and very overkill in some ways. This is matrix multiplication. If you're not familiar with this notation, it's actually not very nice. What I really recommend like learning if you're gonna deal with like lots of dimensions and stuff is probably, if you're doing that in Python, I would recommend learning inops and einsum for this kind of thing, because this notation is really unclear, as I'm sure you can tell. But what we're doing is we're just multiplying our data by our weights. So, it is not clear, and I appreciate that. And then what we're doing here is we're doing this signal transformation. So we're actually not using a function to do it, we're doing it ourselves. And this is going to return all of the probabilities that we need. So I'll run that again. When I say run that again, it should, oh yeah, it should run now. So we can see here, this is finished up here. We can see the average loss from when we fitted it. And hopefully you're familiar with this kind of thing if you've built models like this before. And this is kind of getting more towards machine learning, right? And if you've worked with like I've been saying, PyTorch or something, lots of this kind of like these words like loss and logits are going to be a little bit more familiar to you. And indeed, you could use a neural network if you wanted and try and get some kind of idea of predictive uncertainty as well. Although I do like Bayesian models because the way they are built is around uncertainty. That is the entire theory. Okay, right. So now we're going to produce some plots. And again, in the interest of time, we've got about 10 minutes left. I'm going to plop in this data here. You can see here, I'm going like, make sure you use the right scalar. And so we're doing the same thing as before here, really. Okay, so we've already defined this constant, so we can just delete that. We're building our bounds up here. We're setting our grid resolution. That's already done as well. We're making sure that we've got the right dimensions. As you can see, I've got a little bit finicky about, and we're generating our posterior predictive probabilities. We've trained on all of this data, we fitted it, and we've now got these output distribution, which will give us an idea of epistemic uncertainty a bit more clearly. And so if we run this, hopefully, yes, we get some nice plots out. Okay, and I do recommend like having a look at this, but it is the same syntax and theory that we've gone through in the logistic regression case, right? So we've got two plots here, really. And I can see no questions so far, so I'm going to keep going. This is the one that we had before. But you can see here that actually the out of distribution data, it's still in the kind of more confident region, and that's not great. But it's much, much better, right? It's much better. We can see here that there's a degree of uncertainty around it, and we can see that even though we've got this linear decision boundary, our confidence, our certainty is introducing this idea of curving away from our data where we've seen it. And this is the epistemic uncertainty in action. And you can see the posterior spread here much more clearly. So this is the like visualization, I would say, is really good, demonstrating this epistemic uncertainty. So this heat map, as opposed to this, which just provides the probability of it being in each class, is the standard deviation across posterior samples. So the standard deviation is just how spread out our data is, right? And so here we can see that there's not much standard deviation. It's kind of expected. Whereas, oh, give me a second. There we go. Yep. And we can see that the bright regions are ones with higher epistemic uncertainty, i.e. near class boundaries, perhaps we can see it creeping in a little bit. But really, this is in areas where we have little to no training data. Okay, so this is where our out of distribution data lives. So if we had data over here or over here as well, we'd be like, oh no. Whereas if we had data here, we would be like, okay, actually it maybe fits in with this pattern, right? And that you might argue is a limitation as well. You might say, well, really we should fit a curve around here and a curve around here, and then everything outside of that should have very high uncertainty. And there are models that would do that for you. But I think this is one of the most beautiful ones because logistic regression is linear, right? So we still have a linear decision boundary, but we've got this more comprehensive predictive uncertainty where we're using our posterior and we're saying, okay, we've got this idea of uncertainty, not just, we're not just got probabilities around like how likely we think they are like belonging to each class, but we've got uncertainty associated with those probabilities, right? And we've done that using the standard deviation across posterior samples. Okay, so instead of having one set of weights, we've got a whole bunch of weights, and where the standard deviation is really, really high across the kind of output that we're expecting, and we can say, okay, we're not very confident, right? Cool. Hopefully that makes sense. The premise is that we've got almost like an aggregation of these weights, or at least like averaging over them, and standard deviation in those weights is very high in these areas. The theory is maybe you would build a model and it's doing some classification for you, and you want it to flag to a human supervisor when something has gone wrong and it doesn't know the answer. And the model that we built up here, let's hop up, would not do that, right? It would not do that. This is simplistic and it doesn't have that level of comprehension, doesn't have any predictive uncertainty. But as we flagged down here, Bayesian logistic regression stays cautious on unfamiliar OOD inputs. Okay, so instead of picking one set of weights, it keeps a distribution of plausible weights, and then averaging predictions gives us less extreme probabilities. Okay, and we get a higher spread. So you can see here we've got that less. Let's get that up again. Maybe I should actually let's split to the right, open to the side. Yeah, that's fine. Okay, I'm going to pull this down here and get the graphs up. I think we'll wrap up in a couple of minutes. This is basically the end. This is good. Okay, and then if I go up here, nope, down here. I want section 4. Okay, perfect. So let's go back to this. Averaging predictions, right? We're keeping a distribution of weights. So that's those posterior samples that we've got here, right? We've got a distribution of plausible weights. When our inputs look unfamiliar, many weight settings are plausible. So averaging predictions gives less extreme probabilities. So we've averaged across here, and we can see that the probabilities that we're getting are less extreme compared to the very much like almost black and white probabilities that we got with just normal logistic regression, right? It had much stricter lines. Well, it was completely linear, even like outside of its boundary, its probabilities were completely linear too, whereas this is not the case here. Okay, and we also get a higher spread across samples. That's this here, higher spread across samples. So the higher spread is just another way of saying standard deviation, right? And so when the data looks unfamiliar, i.e. outside of this familiarity range here, many weight settings are plausible, yeah? And that gives us a higher spread. That higher spread is kind of what we call epistemic uncertainty. And we can see here that we're kind of flagging those out of distribution data points really clearly. Awesome stuff. Okay. I'm glad that someone else thinks this is awesome as I do. I'm such a nerd for this. For me, sometimes the error says previous execution ended unsuccessfully. I've actually not heard that error before. Let me Google that. Previous execution ended unsuccessfully. I feel like this is probably like a notebook error. Are you in Colab? I'm guessing you're in Colab. If you're in Colab, it's probably that. It's probably that like you accidentally disconnected from your runtime. The runtime is just like, you know, whether you're like continuously connected to the device that you're running your code on or not. So that might be it. That might be it. So what I'm going to do is I'm going to save this. I'm going to check if I've got anything else to pop in on section 4. Nope. Okay, I'm pretty happy here. Cool. So we could choose some policy here to flag these, and we could do that using, for example, like the 95th percentile. The 95th percentile. There we go. On our in distribution data, and then anything which is outside of that is definitely not going to be in distribution. That's the theory, right? And so we could build something that does that. I don't think we have time to do that now. Got a couple of minutes left. What I might do is I do have a notebook open from earlier, which maybe has some other bits and pieces that would be interesting to talk through. Okay, yeah, let's do that. So if let me stop sharing my screen here. What I am going to do is quickly completed section 4. So this is basically the end. What I'm going to say is, if you didn't check in at the start, please do check in. I know that the link is a little bit up in the chat. I can say it again if anyone needs it. And thank you all for coming. I love to hear feedback on what you thought. It's super useful for me. So please do head along to mlh.link/GHW feedback so I can make sure that I'm doing the best workshops for you. I love to hear, yeah, any thoughts, any improvements, any like themes or ideas, or concepts that you'd love to have a workshop on is also super encouraging. You are using Colab? Yeah, it sounds like this is a Colab specific issue. I would maybe disconnect your runtime, reconnect it, and then run everything again. That would maybe solve your problem. Okay. All right. So this is pretty much done. I'm going to stop sharing my screen, and I'm going to reshare my screen. I'm going to share this notebook. Okay. So this is a run through that I did earlier. And I mentioned earlier this idea of an ensemble model, where instead of just like producing a distribution or a posterior, right? And so you have this kind of like concept of the weights and having a distribution over those. Instead, you can just like ensemble models directly, right? So this is a whole bunch of code that does that. Where does it start? This is not what we want. This is, yeah, so this is where we got to just now. And if we keep going down, we could build an ensemble model, and we could do that with like a logistic regression model and also like a random forest classifier. You may have come across those before. This is like not linear, right? And so what it can do is it can produce curves which don't go in a straight line. And you can see that it's done it here. And you might be like, oh, this is much better model. This is much better. It's still only got one decision boundary. There are like other things that are better for this. So like support vector machines are maybe good for this. Let me see if I can find a link for them. Yeah, if you like just, yeah, you can head along to this, and this maybe gives you some information on SVMs. I would say they're good for this kind of modeling where you've got moons, but I'm not sure about the uncertainty pulling out of them will be so good. But you can see here like an ensemble, it's not linear, right? So it gives it a big advantage, but it's even more strictly kind of identifying out of distribution data. And so if we wanted to kind of try and split off the aleatoric and epistemic data, we could do that too. There's a bunch of different bits and pieces that we can play about with. You can see this is not always perfect though. Like this is still the reliability curve. It's still getting lots of errors. So there's things to work on. We can flag them though. And I mentioned this, if you put in like a percentile, this is what I was talking about, you can flag them. And you can see that we perfectly flagged all of the out distribution data. There's some which kind of we can see the model is not sure on here. And I would say this is leaning towards aleatoric data, right? Aleatoric uncertainty even. Okay, perfect. Okay, with that, I'm going to wrap up. Thank you all so much for coming. The next thing to head along to is, I think it's a wonderful workshop on making better hacks faster with GitHub Copilot. That's now. Head along for that. It's going to be a super great time. I'm not sure who's running it, but I'll probably pop in. So should be really good. Very excited. And thank you all for coming. I'll see you all later. I'm Quinn, and I'll catch you at the next stream. All right. Bye-bye, everyone.